How's it going, Accelerated Chemistry? This is Mr. Spurk, and this is your Chapter 19, Section 5 notes on salts in solution. So we're going to talk about salt hydrolysis. Universal indicator was added to these 0.10 molar aqueous salt solutions. Based on the indicator color, the solutions can be classified as follows. So all the way on the left, we have ammonium chloride, and it is acidic, a pH of about 5.3. We have sodium chloride in the middle with a pH around 7, and sodium ethanoate or sodium acetate is basic with a pH of about 8.7. And that universal indicator allows us to see the color change as the pH changes. So if we look at this acid-base titration, we've looked at this in the last section. So one curve is for the addition of sodium hydroxide, a strong base, and that's the purple curve. And ethanoic acid or acetic acid is the weak acid, and that is the red curve. An aqueous solution of sodium acetate exists at the equivalence point. So here's our equation. We have sodium ethanoate plus NaOH yields sodium ethanoate plus H2O. The second titration curve is for the reaction between hydrochloric acid, which is a strong acid, and sodium hydroxide. That's the purple curve. And this is the one that we looked at in the last section. The pH at the equivalence point for the weak acid and the strong base titration is basic. That top equivalence point, or equivalence point A, for a strong acid strong base titration, the pH at the equivalence point is neutral. This difference in pH exists because hydrolysis occurs with some salts in solution. In salt hydrolysis, the cations or anions of a dissociated salt remove hydrogen ions from or donate hydrogens to water. So it's taking away some of those acidic H+ ions. Salts that produce acidic solutions have positive ions that release hydrogen ions to water. Salts that produce basic solutions have negative ions that attract hydrogen ions from water. Sodium acetate is the salt of a weak acid and a strong base. The acetate ion is a Bronsted-Lowry base, which means that it is an H+ acceptor. It reacts with water to form acetic acid and hydroxide ions. This process is called hydrolysis because a hydrogen ion is split off of a water molecule. So we have that acetate ion reacting with water to give us acetic acid and the OH-. So this is hydrolysis. In the solution, the hydroxide ion concentration is greater than the hydrogen ion concentration. Thus, the solution is basic. If we look at another example, the ammonium ion, or the NH4+, is strong enough acid to donate a hydrogen ion to a water molecule. So here we have this solution being acidic. To determine if a salt will form an acidic or a basic solution, remember the following rules. A strong acid plus a strong base will yield a neutral solution. Strong acid plus a weak base will yield an acidic solution. And a weak acid plus a strong base yields a basic solution. So basically, whichever one is strong wins, and if you have two strongs together, it's going to be neutral. So now we're going to talk about buffers. And I think buffers are probably one of the most complex and most challenging topics in chemistry. So we'll definitely spend a lot of time on this in class. So consider a solution containing 0.20 molar each of ethanoic acid and sodium ethanoate. This solution has a pH of 4.76. If you add 10 milliliters of 0.10 molar sodium hydroxide to 1 liter of the solution, the pH increases 0.01 pH units, only from 4.76 to 4.77. This is a relatively small change in pH. If 10 milliliters of acid had been added instead of the base, the amount of change in pH would have also been small. The solution of ethanoic acid and sodium ethanoate is an example of a buffer. A buffer is a solution in which the pH remains fairly constant when small amounts of acid or base are added. A buffer is a solution of weak acid and one of its salts, or a solution of a weak base and one of its salts. A buffer solution contains one component that can react with hydrogen ions, or the hydrogen ion acceptor, and one that can react with hydroxide ions. These components act as reservoirs of neutralizing power that can be tapped with either hydrogen ions or hydroxide ions and are added to the solution. The ethanoic acid ethanoate ion buffer can be used to show how a buffer works. When an acid is added to the buffer, the ethanoate ions act as a hydrogen sponge. As the ethanoate ions react with hydrogen ions, they form ethanoic acid. Ethanoic acid is a weak acid and does not ionize extensively in water, so the pH is a very slight change. So we have those ethanoate ions snatching up those H+ ions, yielding ethanoic acid. When hydroxide ions are added to the buffer, the ethanoic acid and the hydroxide ions react to produce water and the ethanoate ion. The ethanoate ion is not a strong enough base to accept hydrogen ions from water to a great extent. Therefore, the reverse reaction is minimal and the change in pH is very slight. So basically for buffers, it's basically a solution that when you add an acid or a base, the pH doesn't change very much. Buffer solutions have their limits. As acid is added to an ethanoate buffer, eventually no more ethanoate ions will be present to accept those extra hydrogen ions. At that point, the buffer can no longer control the pH. The ethanoate buffer also becomes ineffective when too much base is added. So basically, it has its capacity. It can hold on and it can try to only change the pH by a little bit for so long, but until there's too much acid or too much base added, then you're going to see a dramatic change in your pH. Adding too much acid or base will exceed the buffer capacity of the solution. The buffer capacity is the amount of acid or base that can be added to the buffer solution before a significant change in the pH occurs. So we can describe buffer systems. So we're going to write a balanced chemical equations to show how the carbonic acid hydrogen carbonate buffer can mop up added hydroxide ions and hydrogen ions. So what we're first going to look at is the carbonic acid buffer. So we have H2CO3, and if we add a base to this buffer, the base is going to take some of those H+ ions. So we're going to be left with HCO3 and H2O. So that's how this buffer would work if we added a base. Now, if we take what we just ended up with after we added a base, and now if we add an acid, so H+ ions, we're going to be left with carbonic acid. So back to the beginning. So this is just a simple way to show what actually happens when you add an acid or a base to a buffered solution. So in review, salts that produce acidic solutions have positive ions that release hydrogen ions to water. Salts that produce basic solutions have negative ions that attract hydrogen ions from water. A buffer is a solution of a weak acid and one of its salts, or a weak base and one of its salts. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry, 2012 edition of the textbook, the resources CD, and pearsonchem.com. This is my last Edpuzzle video for you guys before I have to leave. So have a great rest of your year, and I wish you the best of luck.